Hello, we are ready to go to lecture 12 and talk about two particular important processes that are the isotherm and the adiabat processes. So these are central processes, as we will see later in the definition of engines, in particular the Carnot cycle. And we are going to see how we can understand those processes for the ideal gas. So you see right now we have developed an understanding of what's going on in terms of the first law of thermodynamics. And in the last screencast, we discussed that the internal energy of a system is a function of state, so it only depends on the state itself and not how we got there. But it can be decomposed as a sum of work and heat. And remember the convention we had that it's positive if the work is done on the system and if heat is provided to the system. But what we realized as well is that this change in heat and change in work are not function of state. So work and heat are not function of state. It depends how we get there. But the sum of them turns out to be a function of state. It's the internal energy. So all this is going to lead us to a number of effects that we are going to start looking at today and in the coming lectures. Another thing that will come to haunt us many times in this course is the problem of reversibility. Reversibility is not part of the second law per se. Nothing tells you in the first law that you cannot go backward in what you're doing. But it turns out to be an important one, and it's actually going to be the central topic of the second law of thermodynamics. But let's not jump the guns too quickly. Let's first spend some time on the isothermal and adiabatic processes. And before we go there, let's talk a bit about reversibility. And we know in physics, if one process is allowed, in principle, the time reverse process is allowed as well. We're not saying that it's equally likely, but it's definitely allowed. Yet, many processes don't seem to be reversible. So they are known to be irreversible. That means that even though it's possible, it does not happen. Okay? So I already mentioned that to you. It's like if you bring cold milk in the coffee, it's very unlikely that you will find a few minutes later that the cold milk and the hot coffee will still be separated. Yet that particular state of matter is possible, but it's not going to happen. And we already discussed this, of course, that the laws of physics are one thing, but the probabilities for them to happen is also important. So the question is that what's the probability of finding this? So so we will see and that how we go there. And then we also know that all those things are related to heat, to release of heat. I don't want to talk about entropy just yet because there is no reason to, but we will see that entropy will allow us to write all these things in a more formal way later. Okay? So the crucial point about all this, everything has to do with the number of microstates that correspond to one given macrostate. Okay, so we are going to discuss that in great detail when we talk about entropy later on. But for now, it suffices to say that everything has to do with probability. So even though a particular physical process is allowed, it's not going to happen because it's essentially totally improbable. And when I say improbable, I'm talking about numbers like 10 to the power 50 probability. So essentially 10 to the power minus 50, which means that it's not going to happen in our lifetime. So let's go back to the example we showed for this, which is the idea of this 100 coins problem. Remember what we did a couple of lectures ago, where we were putting 100 coins, which were balanced coins, the quarters, for example, like shown here. And of course, the number of configurations is each coin getting either head or tail. Therefore, we have 2 to the power 100. Okay? So, and we discussed this, and each particular microstate, so each particular configuration, if you will, has a probability of 10 to the power minus 30, which is 2 to the power 100, right? It's just that each configuration is equally likely. Therefore, the probability of each is 1 over 2 to the power 100, which is 10 to the power minus 30. Okay, good. Okay, now we also know that this is the microstate. Now, if the macrostate, which is a different question really, is how many heads and how many tails I have on my system, we know that is a totally different question. And as you know, there are only a total of 101 such possibilities, right? If you don't remember, please go back to the lectures where we discussed this. But the point is that this macrostate, which basically answers the question how many heads and how many tails I do have, is a very much different topic. And of course, the most likely macrostate I'm going to measure are those that correspond to the most microstates. I don't have to go back to this discussion. We've had it before. Now, what I didn't do in that discussion is to discuss this through the lens of reversibility. So let's try to do that now. So suppose that you start and you put all your coins in the bag with all the same. Let's say all the heads are facing upward. Let's say so. That's one of the many microstates, which is, as I said, very likely. Very unlikely. Okay, but you created it, so that's what you decided to do. Now you mix the bag, and you mix it well, and then you calculate the number of heads and tails. Clearly, you're going to most than likely observe a macrostate that corresponds to a large number of microstates. So something close to having the same number of heads and tails. Okay. Even though you started with all heads, for example. All right. Now, if you do the same, if you prepare your system randomly, just a random microstate, and then you do the same experiment, and again, the probability of finding a given macrostate will be given by the number of microstates that correspond to it. The point is that whatever you do, it's extremely unlikely when you shake the bag that has all the random configuration. It's very unlikely you will find all heads or all tails. In fact, it's as likely as 10 to the power minus 30. So from a perspective of somebody who does not understand statistics, or somebody who does not understand the difference between microstate and macrostate, we have an irreversible process. So the fact that you have all well-ordered structure, okay, which is all heads or all tails, and then you shake the bag, and you will never, ever, well, at least in principle, you will never, ever, because the probability is so small, find all heads or all tails after a good shake, seem to be from the observer, from the person from the macroscopic perspective, it seems that the system is irreversible, okay? And it is irreversible because that particular state of all heads or all tails only correspond to a very small amount of microstate. In fact, each of them correspond to one single microstate. Okay, so this is the idea. This is the idea of irreversibility from a perspective of the observer. From the observer, it's just that a well-ordered system usually corresponds to very few microstates, and that's the reason why disorder seems to be prevalent. Disorder is prevalent because it corresponds to more microstates. That's really the reason, and you can understand that with the 100 coins. Okay, so just to say, we have 100 coins. The numbers are already extremely tiny. Imagine that we have a macroscopic amount of material. It's going to be even worse. Okay, so we can come up with a very important principle. And the principle is that the statistical behavior of large systems seems to be to drive many systems in an irreversible direction. So if you do not think in terms of microstate and macrostate, it looks almost like something is rigged, but it's not. It's just a matter of probability and the number of microstates that you have for a given system. Okay, so that's the reason why it looks like you have an irreversible direction. I would like to add something though here. Remember the system that I mentioned to you, that we would create a random distribution, the random configuration before the shake, right? I mentioned that. And then we shake. I have to say that that particular random state is just as unlikely to be found again, okay, that where we have labeled every single coin is as unlikely to be seen again as the one that correspond to all head and whole tails. Remember, only if I can identify the different coins. Okay, let's move on. So let's talk about what a reversible process is. So reversible processes are very important, and people have been trying to understand reversible process for a long time, especially in the design of engine. Because in design of engines, and I always portray this as the people who are trying to develop the steam engine, you know, like to when the beginning of the railroads. You want to waste as little heat as possible. In other words, whatever you burn, coal or whatever you burn, you want to get as much as that energy transformed into work, because you know that if some of it is wasted into heat that's transferred into the atmosphere or the surroundings, this is a form of energy that has not been transformed into work. So you would like to have an engine as efficient as possible, and it seems that that doing this in a reversible manner might be a good idea. This said, it's really possible to convert energy irreversibly into heat, of course, and for example, that will happen when we use a very fast process. So the fast process will mean that your system will never be in equilibrium until, of course, you reach the end of your process. So this means that you are creating a situation where your system has, as if you will, a finite step during the process of transforming, let's say, heat into work or work into heat. The best way to look at this is that if you go really quickly at trying to compress a gas or trying to compress even a fluid, you can create shock waves. And a shock wave is, of course, a form of energy. So that's an energy that you obviously can't use as work. Okay, good. So let's try to think about a reversible process a little bit more. So if you go fast, it seems that you cannot really do a reversible process. But what if you go slow? Well, actually, if you go really slow, I mean, when we usually say it's extremely, extremely slow, you can actually have a reversible process. And that's actually when the gas, for example, if we talk about the ideal gas, is the gas remains in equilibrium throughout the entire process. In that case, the changes are so small, so they're actually infinitesimally small, like a delta, a du, right? That the system remains in equilibrium throughout the process. And so what happens is that you have an equilibrium state, that you start from an equilibrium state and you end to the another equilibrium state, and those states are constantly in equilibrium. Okay, so the change between the system throughout the system are infinitesimally small, and therefore you have a reversible process because you can always go forward and backward. That's the idea at every step of the process. Okay, so we usually call such a process a quasi-static process, because quasi means, you know, almost. And it's almost static, so it almost doesn't change, but it goes extremely slowly. Of course, for practical purposes, that's not very simple, but I mean, that's not a very simple process to do, of course, because if it takes an infinite amount of time to do a process, this is not really something that's good for experiment. But in principle, we can do it. Okay. And one thing that's sometimes a little bit confusing for students is that they say, well, heat is bad. Heat is associated with entropy and reversibility, all that kind of stuff. Well, you know, I have to be clear. The first law of thermodynamics means that if we have this reversible process, so if we transform, we can definitely transform heat into work and work into heat, right? So there's no problem. Heat can certainly be absorbed or emitted in the process. In fact, it better be, because if heat cannot be absorbed or emitted, nothing is really happening. Remember that the change in internal energy is the change in heat, is the transfer of heat and the work done on the process. So that's certainly important. And so we need to remember that that's the difference between a reversible process and an irreversible process. One is done quasi-statically, is quasi-static, and the other one means that we are out of equilibrium throughout the process. Okay. All right. So one note that's very important, and of course it's kind of obvious, but let's remind you that one particular good property of a reversible process is that you can run it in reverse, okay, by definition. But this is an important point because that means that we can actually use that effect. We can use, of course, we're using the same equations in that case, and this is something we will use a lot when we look at the engines in the Carnot process, okay. So what we will do in this course is we are going to talk a lot about reversible processes. I have to say that it's an approximation. Sometimes it fails miserably, but this is an approximation we must make because this is the only way we can actually handle the mathematics is when we consider reversible processes. And so of course I will say that when we move along. So when you study thermodynamics, try to always be very critical of what you write. And being critical means think about what's reversible, what's not, and why you can use an equation. And this is time for me to open a parenthesis here, which is going to be important on the next slide, in the next few slides, is that thermodynamics is a wonderful example where you have to know exactly why you are writing an equation. Some equation may look like they should be used without much worries, but in thermodynamics, every single equation has kind of a trick to it. When I mean trick, I mean there are always conditions under which the equations are valid, okay? And so those validity can be the type of system I have. For example, we are going to work with an ideal gas, which is of course an approximation as well. We are going to work with reversible processes, which is also an approximation as I just discussed with you. So it's very important that each step that you actually know what you're doing. And of course, it is also the role of this screencast to provide that information. So I will do my best as we move along to tell you about all these things. So let's try to see a first example of this general philosophy. And we are going to talk about isothermal expansion of an ideal gas. Okay? So just like everything else we do, what's very important is to understand the terms that we are using. Isothermal, as you know, iso means the same, like an isosurface, isocontour, and stuff like that. So isothermal means at the same temperature, okay? So we are going to work at a constant temperature. So remember, we are talking about a system, and the system is whatever we decide it to be. In this case, we are going to look at the gas that's going to expand, in a gas that's in a certain volume. And we are going to make sure that we are going to do an isothermal process. Isothermal process means there is no change in temperature. Now, this is where things have to be factored in from the previous lectures. If you remember, I kind of insisted on this in particular about if you have an ideal gas, which is what it is about here, the variation in internal energy is the heat capacity at constant volume times dt. Variation in temperature, right? That's what we discussed. So this is an important thing to remember, and please, if you don't, go back to the previous lecture. I believe this is where we did this. Okay. Now, du equals cv dt. If we have an isothermal process, that means the temperature does not change by definition. Therefore, for an isothermal process, the total energy, the total internal energy U does not change. So we can use a delta U here. Why do I use a delta U? Because the delta U means between two systems that are not infinitesimally small, close to one another, the variation through an isothermal process lead to a conservation of internal energy. It's extremely important to note that it's only true for ideal gas. Remember, I discussed this, why du was not necessarily equal to cv dt if it's not an ideal gas. Let's not worry too much about this at this point, but remember that that's what we discussed. And also that's good, because this is a typical type of process where the internal energy does not change. And in order to do that, we use the equation du equals cv dt. Okay, Now, we can go further, because we also know the du is dq plus dw. In other words, change in internal energy is due to the sum of the change in heat, so the heat positive if it's provided to the system, plus a change of work, which is positive if it's applied to the system. So this is the first law of thermodynamics. So first law of thermodynamics is du is equal to dq plus dw. In other words, if du is equal to 0, that means that the change in work, so basically the work that's performed on the system, so for positive work, is equal to minus the heat that's provided to the system. So minus the heat that's provided to the system is the heat that's taken from the system, right? So basically the work done is equal to done on the system is equal to the heat that's transferred from the system. So in other words, whatever comes in has to come out, because we know that the total energy is equal to 0. Okay, so you see the different processes that we already had to use here, right? We had to remember the first law, we had to remember that we have an ideal gas, and also we have to remember that we are talking about different process at constant temperature. So let's keep going. So this text here is just what I told you. Now, if we have a reversible process, we know that the work done on the gas, so basically the fact that the volume of gas can change, right? The volume of gas can change. That work is minus PdV. And remember, minus PdV is pressure times the change in volume. This is nothing else than the work that we get from force times the distance that the force moved along, right? F dot dx is PA dx, A being the surface, so A dx is the volume, right? So this is the idea of, remember. The minus sign comes from the fact, and I'm reminding this to you one last time, is the volume increases, or the volume decreases. That means that work is done on the system, okay? So delta dV is negative, so the work done on the system is positive by convention, therefore the minus sign is needed there. All right, very good. So we have those equations. So what do we do now? So let's try to see, because we see that even though we have an isothermal process, and I just want you to wrap your head around this, even though we have an isothermal process, because we allow work to be done on the system, heat has to be transferred to the system. Okay, so let's try to calculate that heat. Let's calculate the heat absorbed by the gas during the isothermal expansion. So we suppose it's an expansion. Basically, work is done. The system is doing work. Okay, so basically the change in work will be negative. That means that the system has to get energy from somewhere, since its total energy is constant, right? So let's calculate it. Well, let's use the equation that we know. The heat change between the initial and final state is simply the integral of dq. Now, the problem we have with this, as you know, q is not a function of state, so we cannot just say, oh, it's q1 minus q2, right? That makes no sense, because we do not have the usual dq that we have studied when we took calculus 1, right? That's not it. However, we know that dq is minus dw, so we can certainly write this, right? Because we have a conservation of internal energy. Now, we also know that if we have a reversible expansion, and by the way, I say reversible because if it were not reversible, let's say that the process of changing the volume was fast, we would have other effects like turbulence, like shock wave and things like that, which would be other term in the energy. But we suppose that it's slow enough that it's reversible, and it can be written minus PdV. That means that we can write this as PdV. Now it's nice because we are talking. This is really nice. We can calculate this, right? Why can we calculate this? But remember, pressure is not a constant. It's not at all. However, we know that's an ideal gas. So P is actually equal to RT divided by V. It's the ideal gas law. So I can substitute And I can get this equation right there, all right? And now it's nice, because R is the constant of gas. We can take it out of the integral. T, we can take it out of the integral, right? Why? Well, because I told you we are talking about an isothermal process. So it's done at constant temperature. So we can remove RT from the integral, and we end up with a trivial integral dV over V, which is obviously a logarithm. So we have RT and logarithm of V2 divided by V1. Okay? So I spend a little bit more time on this with you, because I think it's important to understand each step. Each step is actually loaded. Okay? It's loaded with conditions and understanding. So if you try to do this just as a math exercise, you are going to fail miserably, because every single line has to be explained by a physical process. This is very often the case in physics, of course, but that's a good example of that. Now, let's try to think a little bit. If we have an expansion, V2 will be larger than V1, and the logarithm will be, of course, positive. That means that delta Q will be positive. So if we have an expansion, heat has to be provided to the system, so heat has to be positive, so we are good there, okay? So this is good. Now, if you do, let's try to think a bit about this equation we got there. If we do a thermal expansion, okay, isothermal expansion, sorry, okay? If we do that, the heat that you need to provide to the system will be RT ln V2 over V1. That's wonderful, right? This is really nice. So the expansion has to be in isothermal expansion for an ideal gas, and it has to be done reversibly. So you know, it's a lot of it's a loaded set of conditions. But we can tell the amount of heat that we needed to provide to the system in order to move it from a volume V1 to a volume V2. It's written right there. Okay. Nice. So what about pressure? You know, I mentioned to you pressure. Pressure is not a constant, right? It's RT over V. But how come it's not a constant? Because remember, this is a very important point. The pressure we set for an ideal gas, pressure is proportional to the internal energy. Do you remember that? We said the P, and it was one of the first things we did, and we also mentioned it when we introduced the adiabatic index gamma. So hold on, is that a problem? If the pressure is proportional to the internal energy, then the internal energy being a constant, the pressure should be a constant, but nothing works then. Hold on a second. This is where the details, the devil is in the details. Because what we said is not so much that the pressure was proportional to the internal energy. We said the pressure was proportional to the internal energy density, okay? So that the energy, the internal energy divided by the volume. So this is kind of a subtle point, but the fact that the energy remains the same is fine, but the energy density is actually reduced since the volume increases, okay? So U does actually change, U being the internal energy density, because the volume changes. Just want to make sure that it's clear to everyone. So we are halfway there. We've done one thing. We've calculated the change of heat, that's the amount of heat that's needed to expand a gas at constant temperature. That's what we did, okay? And we just had to apply whatever principle we've learned. Now, there is another type of process that we can look at. It's the one where there is no exchange of heat with the surrounding. So you totally isolate your system so that there is no exchange of heat with the surrounding. Of course, in that case, the temperature can change if work is done, right? Because we're going to see that for a second, but you can think a little bit about the problem. So this is called the adiabatic expansion of an ideal gas. And in fact, an adiabatic change is actually correspond to a change where there is no transfer of heat whatsoever. So the system is isolated from its surrounding. So dq equals 0. Okay? So this is another, remember in the isothermal change, we just said that we just said that du was equal to 0 because temperature was constant. Okay. Now here in an adiabatic system, we are isolating it completely from the surroundings, so that there is no heat that can be exchanged, and that means that dq equals 0. That means from the first law, the du is equal to dw. Okay. In other words, the change of internal energy is completely due to the work done by the system. Okay, because here we're talking about expansion, so the expansion means the system is doing work. So basically, it's going to be should be a negative number, right? Because if work was on the gas, that means that the gas would actually be compressed. Here it's an expansion of an ideal gas. Good. So in that process, of course, remember our usual equation for an ideal gas is du is Cv dt, and dw for a reversible system is, for reversible process, is minus pdv. So what we end up is this equation, du replaced by Cv dt, which is equal to minus pdv. And one last step here, I could have done one more step, but it's all written in the second equality, is that we can replace again P by RT over V from the ideal gas law. Okay, so this is quite nice because we have Cv dt is equal to minus RTV dV, and we can integrate this because on the left-hand side we are going to end up with dt over t, and on the right-hand side we are going to end up with R over Cv and dV over V with a minus sign in front. So, of course, dt over t and dv over v can be integrated on both sides, and we end up with the situation where the logarithm of the ratio of temperature is going to be equal to minus r over cv with the logarithm of the ratio of the volumes. So that equation is somewhat different from the one we just saw, because in the previous one we saw for the isothermal expansion, we also had a logarithm of V2 over V1, but it was proportional to the change of heat. Here, it's proportional to the logarithm of the change of the ratio of the difference in temperature. But it's not over, and this is probably the most important 5 minutes of this screencast that's coming up now. We are going to we don't like to use CV there. I mean, maybe we can do something different. Remember that we introduced the adiabatic index being 1 plus R over Cv, right? That means that I can replace R over Cv in the red box by gamma minus 1, right? So since there is a minus sign in front, it's going to be 1 minus gamma. So we get this. So we get a logarithm of T2 over T1 is equal to 1 minus gamma ln V2 over V1. Remember, gamma is, for an ideal gas, is going to be 5/3. Okay, but let's not worry too much about that just yet. Okay, let's keep gamma right now, since it can change values if it's not an ideal gas. Now we can put all the variable that depends on the final state on the left, and all the variable depend on the initial state on the right. And using the properties of logarithm, we find that the logarithm of T2V2 to the power gamma minus 1 is equal to the logarithm of T1V1 to the gamma minus 1. Wow, that's very nice, because that means that in an adiabatic expansion of an ideal gas, it looks like T times V to the power gamma minus 1 is a constant, right? Since if the two logarithms are constant, that means the numbers themselves are constant. So what we just proved is that TV to the power gamma minus 1 is a constant in this process. So in an adiabatic expansion of an ideal gas, TV to the power gamma minus 1 is a constant. So usually we do not so much use that expression, at least it's what we're not going to do for the Carnot cycle. Instead, we replace the value of T by what we obtain from the ideal gas law, actually, which is PV equal NKBT, remember? So we are replacing, we know that T is proportional to PV, okay? So since it's proportional to PV, we can replace T by PV, and it's going to be equal to another constant. It's not the same constant on the second line. So of course, one of the V is going to simplify with the minus 1 in the power gamma minus 1, and we end up with an extremely important equation, which is PV to the power gamma is equal to a constant. And this is really, really, really crucial. So we know, and I'd like to spend a second here, we know in an isothermal process, we can calculate the heat we need to expand the system by a certain volume, okay? Now, if we have an isothermal process, the other equation we have is the ideal gas law, which is on the bottom right of this slide. So if we have an isothermal process, the right-hand side of the equation, PV equal NKBT, is a constant. So for an isothermal process, PV is a constant, okay? Clearly. But for an adiabatic process, just like this one here, PV to the power gamma is a constant. These two equations are, if you understand the difference between these two equations, your life is going to be so much easier when we study the Carnot cycle. Okay? Let me try to explain to you why. Okay? This plot is obtained from the book, and I'm going to highlight a very important feature of this. So remember that gamma is usually significantly larger than 1. Okay? In fact, for an ideal gas, it's 5/3. We've established this. So the adiabatic lines, so those that corresponds to no exchange of heat, correspond to PV to the power gamma is a constant. The isotherm lines, which is those where we do not change the temperature at all during the process, are PV equal a constant. Now, here's the idea. If gamma, the fact that gamma is larger than 1 means that if you take a certain value of V, okay, a certain value of starting V, PV to the power gamma is going to decay much faster than PV is equal to constant, right? So the PV to the power gamma will decay much faster than PV. That's the reason why the dashed line that you have on this plot go down much faster than the solid lines. So let me highlight 2 of them for you. So this one is an isotherm. So the isotherm are solid lines, right one there. And I'm going to look at the other lines that start from the same point on the PV plot. And this is going to be the blue line here. And you see those two relationship. One is PV is equal to a constant, which decays not very quickly. And the other one is PV to the power gamma, which is a constant, which itself is going to decay much faster because gamma is larger than 1. And this is something that I'd like you to spend some time to convince yourself about. Because what we are going to try to do when we are going to study engine on the next lecture is to actually travel along those lines, okay? Our goal will be to try to create a cycle in this PV space. And in order to do that, we need to have common starting point and ending point. And what we will do, and I'm going to keep the suspense until next time, what we will do is travel along those lines and in such a way that we are going to alternate travel on the adiabat, so the adiabatic process, and travel on the isothermal process. The goal being that we want to create a cycle where we always have, points on the PV curves, so that basically you are increasing the volume, you're decreasing the volume, increasing the volume, decreasing the volume. And during that process, you of course want to create work, okay? And you also include heat in that system. So you're going to inject heat in the system during an isotherm, and in fact you're going to have to release heat as well. We'll see that it's impossible to do this without also releasing heat. And we are going to be able to essentially create a cycle on this plane, on the PV plane, by jumping, well, it's not really, jumping from an adiabat to an isotherm, and that's going to make sense. And so you will understand the Carnot cycle more as I would say like a schematic than it is about the math. But what I would like you to take home from this lecture today is the PV is equal to a constant for an isotherm, so that you already knew from the ideal gas law. And PV to the power gamma is a constant, which is something we demonstrated today for an adiabatic process. So remember the definitions we came up with: adiabatic, isotherm, and all the good stuff that comes along. Thank you very much for your attention, and see you next time.